kind of part, and they just got them, so I haven't heard back like how
All
the
right,
feelings are so far. But
Tom, so give me a minute explaining about kind of like your jazz involvement, as you know, here at Michigan Tech, but also what your kids are playing and how old they are.
So I played everything. There was one time at school, I think it was my senior year of undergrad, I played music 40 hours a week. And that's not an exaggeration, because I was doing pit orchestra for one of the shows we did, Cabaret, which was, I think, that was really well done. I really liked that. So I did pit orchestra for Cabaret. I did Kiwanis Symphony Orchestra. I did the jazz band. I did the wind band for as long as I could. And then I was in jazz tech for a couple of years. So that was the jazz group a smaller group, and we went out and did gigs. Like we did usually after concert shows down at the library bar, and we'd play till 2 o'clock in the morning. We played all over. We played at some of the casinos sometimes, and we played all over, like paying gigs. And yeah, for a while there was a few weeks there where it was like 40, but if you count rehearsals and performances, because like performance week for some of these shows, it was 40 hours per week just of music sometimes.
That's great. No, this is inspirational to any musician. Music intersects engineering so kind of strongly in the brain. And so your kids, are they playing horns? Have you made
So
you can only play horn?
My oldest, yeah. So my oldest, he plays clarinet.
Oh, not the trombone.
Not brass. And it's okay. I tried not to influence. I tried really hard not to influence. He's his own person. He gets to choose. And he chose clarinet, and I think partly it was because it was small,
Clarinet.
and he liked the idea of having a small thing to carry around. So, and he's really enjoying it. But now he's recently in middle school, he's had the opportunity to try the bass clarinet, and he's really taking off on bass clarinet now. And my younger son, who is a bit more, for lack of a better word, loud, he's just starting the trumpet. So that, like, for years, my wife and I looked at him and said, I think he's a trumpet player. And sure enough, that's what he chose. So he's just starting, but he's got hot cross buns going, so that's good.
No, that's good. All right, so we're getting close to the hour. Sue, go ahead and start recording. All right, so we've been chitter chattering. We always so this is Husky Bites. My name is Janet Callahan. I'm the Dean of the College of Engineering and the sort of chief host of Husky Bites, which is a webinar series that features a person each Monday night. We go live at 5:40, so if you want to join us for a conversation, you're welcome to do that. And then starting at 6, we kind of teach you something serious, and then we have Q&A, and that's kind of our format. We started it this summer in a pandemic. We're still in a pandemic. We're keeping it going because I've been having so much fun with it and getting such great, comments from people who watch. So we sort of feature a different department or college each Monday. And this evening we're featuring electrical and computer engineering. And Dr. Paul Bergstrom is our featured speaker, who will be introduced by Tom Wallner. And so it's my pleasure right now to introduce Tom Wallner. Tom Wallner is my co-host this evening, which means he gets stuck carrying the conversation if I drop out, and he's in charge of all the Q&A. Co-hosts are typically, but not always, alumni. And in this case, Tom is an alumnus. He earned both his BS and his MS in electrical engineering here in the years 2002 and 2004. In addition to that, he played it avidly as a musician, a trombonist, and possibly other instruments as well, which we were just hearing about. He also was a leader, being president of the student chapter of IEEE, which is the basic society for electrical engineering. He led as a student the initiative to renovate the what is called the 809 IEEE lab that was sponsored by Kimberly Clark. And if I was to sum up, well, no, in addition to this, Tom achieved renown as building a notable loft in Douglas Houghton Hall in 1999-2000. And unfortunately, we don't have any pictures of that to show you. But to summarize, I guess I would say Tom is a builder. And so he earned his intersection with Dr. Bergstrom is he earned his Master of Science degree working in Dr. Paul Bergstrom's lab, who we're going to hear from shortly. I think this is where he met the love of his life, Jin Zheng Wallner, who I hope is listening this evening.
I think she may be herding boys right now. I think it's homework fine. Time. So yeah.
These are all recorded. We can watch them all later. Last week's Facebook Live was a bust. We couldn't get it to go. We don't know what happened, but usually they're also on Facebook Live. Anyway, just to finish off the introduction of Tom, Tom started his postgraduate degree, career working at Sandia. Then he spent a very long stint at IBM doing microelectronics R&D. He is now a photonics tester. He is an R&D engineer for PsiQuantum, which is building the world's first useful quantum computer, and they are following a photonics path. And that's the full extent of what I can explain about Tom Wallner. So Tom, you go ahead and take it from here.
Thank you. You hit all of that. That was pretty much spot on. Yeah, the opposite of what you see most quantum computing companies and research groups doing now, we refer to as matter-based quantum computing. So they use some sort of ion, or they're looking for some sort of transition or a spin of an electron. Everything is matter-based. And the problem with matter is that temperature causes vibrations on all of these things, and they become very, very noisy, and you have to cool them to ridiculously, insanely low temperatures. And if you use light, it doesn't have those problems. And so that's why we use light at PsiQuantum. So yeah, so thank you for that introduction. It's all spot on. The only thing I have to add is I think, one of the reasons I did go to Michigan Tech was I liked the snow. I was, you guys were talking about snow before, and I was pretty jealous about that, not gonna lie. And and I've got a whole nother story for any time if you want to hear it, about how snow kind of kick-started basically my entire career, but that's for another time. So I have the honor of introducing somebody who is near and dear to me. Janet and I had not met before a couple days ago, and I sort of joked with her. She said, so yeah, okay, Tom, nice to meet you. And have you ever met Paul? Do you know him? And I said, no, I don't know him, never heard of him. And she took it as for real and started explaining to me all about Paul, about how he's a faculty. He's been around since about, what was it, 1990, or no, sorry, 2000 even, yeah. And how he's in the electrical engineering department. He does all kinds of microfabrication things, and et cetera, et cetera. And I finally had to break in and say that, like, no, I get it. I was one of Paul's first students, even as an undergrad. And like you mentioned, my wife was also one of his students. And I like to joke that my wife has pretty eyes, because, in the lab, when you're in the gowns and stuff, this is all you can see. And so she had very pretty eyes in the lab. And so that is not even, it's not really even hyperbole there. That's no joke. So it's my pleasure to introduce Dr. Paul Bergstrom, who is my advisor and mentor. And I also call him a friend. And so take it away, Dr. Bergstrom.
So I guess I need to share my screen, don't I? So let me get that taken care of. So what I'm going to talk about, the title of my talk is, let's see if I can find what I'm supposed to find here.
And remember, folks, you can post questions along the way in the Q&A, and we will stick around to answer the questions afterwards. But you don't have to wait to the end to type in your question. As it occurs to you, you can type it in.
And Tom, you interrupt me if I get too far off field in jargon.
Peanut gallery. I'll be throwing the peanuts. Don't worry.
There
Yep,
we go.
I got
Okay.
you.
You do your best. So I titled my talk Nanoscaled Epic Fails, Learning Through Failures Using the Scientific Method in Experimental Research and Designed Experiments. And the reason I did this is because we have to recognize that not all failures are bad. Failing is part of learning, and we need to learn from our experiences. So experimental research builds off of this significantly. So the point is, you can have success through failing. And that makes me think a little bit about the Cheshire Cat quote in Lewis and Carroll's Alice in Wonderland. If you don't know where you're going, any road will get you there. But that's not the scientific method. And I want to ask you guys what the scientific method is. So this is maybe a rhetorical question, but this is something that's kind of like your preliminary quiz question for the talk, is to think about what the scientific method is. And Tom, I don't know if you want to give me your thoughts, or if I should just go ahead and launch what I would present as.
I view it as observing what's around you and making some sort of prediction about something. And then my favorite part is the experimentation part, right? I'm an experimentalist.
Sure.
Of trying to see if your idea actually works.
So that's a great kind of framework, and there's lots of different definitions that people have proposed regarding what the scientific method is. They have lots of different steps, but all of those definitions include these 5 main categories. There's a purpose to the work that's being done. You know where you currently are, or you know what the understanding is now, and you kind of know where you want to get to. But you don't know exactly how to get there. So the purpose is the 2 endpoints, and the hypothesis is the path to get there. So in order to follow that path, we have to test that hypothesis, and that's where the experimental method, or where the analysis of the work comes in. You follow the path, and you follow all of the dead ends, all of the blind alleys that you find. Then you have to understand what's going on with it. You have to do the analysis and consider and chart the path as you move forward. And then once you have that, then you can make some conclusions based on that to determine whether you're on the right path, or whether you have to follow some alternative path that you didn't consider when you started out on the starting point. So it's not exactly the Cheshire Cat not knowing where we're going. We know where we're starting, and we know where we want to be, but we don't know exactly how to get there. So the experimental method and the scientific method is all about figuring out how to get to that final point. So I'm going to talk to you about nanoscaled, micro and nanoscaled technologies. And I just wanted to throw this slide up to give us a little bit of a perspective regarding what things are at kind of different scales. So there are natural things that we see at exoscales, which are kind of the scales of the universe, all the way down to the scales of atoms and subatomic particles. So the scales of atoms are on the order of 10 to the minus 10, or angstroms. But there are many man-made structures that also include these same sorts of scales. If we look at structures anywhere from centimeters down, we can look at structures that have been designed in kind of the millimeter to micrometer scale. Those scales relate to things that would relate to microelectronics, maybe the pixels on your digital camera, or some MEMS structure, maybe the accelerometer that is controlling the airbags in your car. But even down to the same sorts of scales that we talk about related to atoms, nanometers or tens of nanometers, where we have structures that we can design and structures that we can work with, which have unique properties that allow us to explore the behavior of the world from a slightly different paradigm. So there are things that man can do to manipulate materials, and there are things that we see in nature that we can use in order to mimic some of those behaviors. So there's a lot of engineering work that's been done at these scales. So
one of my favorite things about that, Paul, is blowing people's minds a little bit when you're talking about, and this is like in my work career, working in, you know, advanced node CMOS stuff where you're worried about nanometer scale things. One layer, you know, like the distance between two layers of silicon is like 4 angstroms, right? That's like an atomic layer.
Right. Yeah.
And
that'd be on
and
the
if you
order of
switch,
eight atoms. Yeah.
right, if you switch between talking about nanometers, and then you say, actually what you're talking about there is about 10 atomic layers. Like
Yeah.
even engineer, like you got to frame your reference sometimes, right? Like you're talking about, we throw nanometers around like 5 nanometers here and 10 nanometers there, and like,
Right.
All right. Here's the quiz question. What is the diameter of a silicon atom?
the diameter of it.
Or radius? Give
Well,
me
I know
anything.
what the lattice constant is.
The lattice the lattice
All right,
is
give me that.
4.4 angstroms. 4.4
Okay.
angstroms. Oh, I don't
Which
have
is-
my cube. Oh,
Which is how many nanometers?
0.4.
0.4.
There we
Yeah.
go. All right. So the spacing of billiard balls of silicon next to each other is 0.4 nanometers. That's
Yeah,
what you're saying.
exactly.
And in semiconductor world, in this device, especially if you have one of the newer ones, you've got devices in there where things in there, not so much the width of them, but the height of them. We're really good at controlling the height of things, right? Could be 2 atomic layers. 8
Yeah.
8 angstroms.
The processors that are in the iPhone 11 and iPhone 12 are working at sub 10 nanometer feature sizes. So the materials in those structures,
About 40 atomic layers.
talking about less than 100 atoms in the diameters of some of these structures. Yeah.
Yeah.
I'm giggling because when I got my PhD, we were in angstroms, but now, Tom, we're in nanometers. Like everybody's moved to nanometers.
Yeah.
Yeah, it's an interesting paradigm shift. It is to think about how the kind of the language has changed even in the last 20, 25 years. In my own career, I've seen that too.
Yep.
Well, and so, Paul,
Okay,
I
sorry.
see a long list of people to acknowledge, and you've worked with a lot of people, and I'm just looking forward to hearing about your nano epic failures.
Okay, so I am going to talk to you about some work that we've done related to developing room temperature single electron transistors at Michigan Tech. And I want to recognize the fact that this has taken place over a modest period of time, about 15 years of research effort, and has graduated 7 PhDs and a couple of master's students out of this as well. So I just want to recognize both my collaborators in terms of faculty that I've engaged with in various aspects of this research, as well as some of our research partners in the Army Research Lab, Dr. Karna and Dr. Malik. Dr. Kare, Dr. Acharya, Dr. Chiam, and Savaikar and Danez and Pani Hazbe, who's actually now faculty here at Michigan Tech. There's a lot of people that have contributed to this work, and so we just need to recognize that this is not something that I want to make sure that people understand the scope of the effort. That there's a lot of work and a lot of time involved, a lot of blind paths that have been resolved, I guess, in this effort. So I'll try to not take too much more time, although I know I still have too many slides. So just some ideas here. So the scientific method learns from what we know, what's in the past, and where we currently are. So the current failures define pathways that we don't think are currently possible. So when I have this impossible star, that means the failures that we're seeing now are probably failures right now because we don't see a path forward along that route. And just some language to help us understand designing experiments or designed experiments allow us to maximize our understanding of a path within an area. So if we want to learn the most we can about studying some type of process or some type of behavior, we want to design an experiment so that we can maximize our understanding over that whole space. And then what comes from that is the optimization. And that optimization allows us to choose the best pathways to move forward. So this is like the road, right? If we know there's some blind alleys, well, we don't want to take those blind alleys in order to move forward. So optimizing allows us to learn from the path, learn from the map that we're building in order to move forward. So the thing that kind of draws this all out is that working at the nanoscale and working on this particular device, the single electron transistor, allows us to look at a lot of blind alleys. And so I'm going to give you some examples of some blind alleys and how they were resolved. And I'm going to probably go a little faster than I want to because I don't want to take too long to do this. And I probably have more than I ought to have in my slide set. So the first thing we have to do is understand a little bit about the single electron transistor. You're not going to get quizzed on this. The single electron transistor uses two quantum tunneling barriers and a quantum dot that allows for the isolation and allows for the isolation of charge carriers on that quantum dot. So by controlling the potential of the quantum dot, the potential energy of the dot, it allows us to force the transition of electrons onto and off of the dot based on the relative potentials of those tunneling barriers. So you would have a source and a drain like you would in a MOSFET, a metal oxide semiconductor field effect transistor. And you'd have a gate in a similar fashion. But in this case, now we have a tunneling effect, which is a quantum mechanical behavior where an electron or a charge carrier can actually move, even if it doesn't have an excess of energy beyond the energy of the barrier. So it can actually tunnel through the barrier under the right conditions. And so this leads to some very unusual characteristics. It allows for a region where the device can have what's called a Coulomb blockade region, which can be changed based on the gate potential that's controlling the quantum dot, as well as something that's called Coulomb oscillations, which are fundamental charge transport that happens under certain current conditions. So that's all we really need to know, is to know that this device, it has an interesting behavior, and that is something that has had interest in the field because it has the potential to allow a transistor action at very low currents. And one of the big problems with the semiconductor industry is waste heat and waste energy just from current flow. So if you have a device that allows you to transport less current and still have a transistor action, this is one of those kinds of devices, and that's why it is interesting to study.
IoT is the buzzword there.
And what does that mean?
Internet of Things. So you have your sensors and whatever scattered all over the place, and you can monitor everything all the time on a little tiny battery or using energy harvested from around you.
Mm-hmm.
You got to have ultra low power devices. It's still a very big buzzword.
Yeah, and it's an area of active effort in the industry as well as in the academy. So we proposed a method using focused ion beam etching as a way of producing these isolated quantum dots and the features that were required for the structure. So a focused ion beam behaves very much like a scanning electron microscope, where instead of an electron beam that we're now producing a beam of energetic ions that have enough kinetic energy that they can ablate or etch materials from the substrate. Now, most of the time, this is a liquid metal source like gallium. Gallium is a very easy metal to use in a focused ion beam system, but there are sometimes other sources that are used. The other nice thing about gallium is it is heavy, and it also allows then for a good transition or a good etch rate of other types of materials, because it's a heavy ion. You can accelerate it in an electric field if you ionize it, and so it's focused and directed to the substrate in the same way that a scanning electron microscope would use. We can control the position of these. We can control the structure. So we started by, our premise was to assumed that we could build an SET based on focused ion beam etching. So our initial studies of this found that there's too much energy. The focused ion beam cannot produce small gaps and small geometries of structures given the amount of heating of the substrate that results as a result of the beam interacting with the substrate. And so this beam is raster scanned over the surface in order to produce the ablation of the material that we want, but this localized heating also causes an evaporation of materials. So if you have structures that are smaller than 20 or 30 nanometers, those structures self-heat so much that they basically evaporate in the vacuum and you're left with nothing. And so because of the profile of the ion beam, this is a model of the profile of the ion beam, there's enough energy that is transmitted to the substrate that it's very difficult to get structures under 100 nanometers just by straight up ion beam etching.
Is there a such thing as sharpening that tip a little bit more? Like, could you go buy a sharper pencil and?
To an extent, regardless of the focus. So the answer is yes and no. So it is possible to produce finer featured ion beams, but even if they are finer featured, they still have this Gaussian tail that is still transmitting energy in an area that's much larger than the tip. Even if your focused energy is very small, there's still an appreciable, roughly half the total energy is still now transmitted over a much larger area.
Yeah.
So we looked at, are there other ways for us to try and solve this problem? And so we considered this and we thought, okay, let's try and understand this about the ion beam and what can we do about etching? What can we do to try and maximize our ability to produce good features? So we did some work there and we worked on this energy dissipation problem and we said, well, okay, straight up etching, the smallest we're going to be able to produce is between 20 and 30 nanometer quantum dots and gaps that are still on the order of probably about 20 nanometers. Well, that's not close enough and that's not small enough for a single electron transistor to work at room temperature. So these are still far too big. The gaps are too big. The features are too big to work at room temperature. We don't have enough quantum confinement and we don't have a narrow enough gap. So we have to come up with an alternative path. This is just not going to work, even if we try and maximize our ability. Now, we did continue working on etching and we were able to get this down considerably smaller, but we still were limited to about 17 nanometers for our minimum features. So we were able to produce structures that had gaps on the order of 17 nanometers that were useful for our devices. And I'll show you some of that work, I guess, here. So doing some understanding of that tail, that energy tail, one of the subsequent students, Manoranjan Acharya, did some very good work to understand that if we now etched through an additional layer, we would be able to produce the features we wanted in the underlying layer down to about sub 20 nanometers, down to about.
And then you remove that like sacrificial layer on top.
And then we remove that sacrificial layer and we're left with the features that were as narrow as we could get. So these structures were roughly about 200 nanometers across. But these gaps, the narrowest gap that he was able to optimize for was about 17 nanometers. That was the smallest feature that we were able to produce in the structure. But so that showed us our limit, for etching. So then we said, okay, it's still not small enough. To get room temperature quantum confinement for the quantum dot, we have to be less than 10 nanometers. That allows then for an electron to be trapped on that quantum dot with sufficient energy such that we can transfer it on, store it there, and then transfer it off under the right conditions. So that was our target. So we said, well, okay, we can't do it by etching. So let's think, what can we do by using this focused ion beam by another way? So focused ion beam systems can also be used to deposit films. So that energetic ion beam can impart energy to a source gas that is a source of metal or a semiconductor, these tend to be methylated kind of gases. So you break down the molecule. These are molecules that contain a species that you want to deposit. You break down that molecule using an ion beam, and you deposit then that metallic or other species on the substrate. And so,
all right, wait. So Paul, I'm a little bit skeptical. Did you really think about this and being like, okay, I'm going to plan for this to happen, or did one of your students just actually notice that nanodots were being deposited somewhere else in the system?
well,
I'm just guessing here.
In the deposition process, we recognize. So this is actually a couple slides that I left out. So that's a great question. In the process, as we were looking at the focused ion beam based deposition, we recognize that there's an amount of time required in order to fully decompose the source gas. But then in that same time that the ion beam is depositing the film, the ion beam is still imparting kinetic energy to the substrate. So it also has an etching behavior. So what we came to recognize is that there is both a deposition and an etching that is happening at the same time in this process. And if we balance the amount of time that that focused ion beam sits in a certain pixel at a certain location, we can balance the amount of energy that is being used toward the deposition, decomposition of the gas, and the amount of energy that's going toward the actual etching of the substrate, etching of the underlying layer, or etching of that deposited layer, as the case may be. And so this was something that we noticed in some of these early images, where we were noticing that our deposited films were not continuous, where we had small nucleates of the material that were isolated from other regions, right? We saw under these different conditions, well, we're getting slightly different behavior in these different conditions. Can we now find the right balance of process conditions to allow us to produce now large arrays of quantum dots that have some kind of nominal size that is going to be in a range that we want? And so that was kind of where we went with this deposition work. So we had been doing some deposition for electrode processing. And so this was something that we did see in part of that processing, but it was as a result of the failure of the etch process that we started considering, are there other ways that we can make use of this, both deposition and sputter etching kind of ablation in order to solve this problem?
You have to really invert your thinking too then, right? Like you go in, you say, I'm going to go etch my thing. And then now you say, like, well, how about I'll just deposit my thing instead, right? Like,
yeah, well, it was a blind alley with the etch as far as getting to the feature sizes that we needed. So we said, okay, let's take a step back and look at what other possibilities we have with regard to this system. What are the types of things that we can do here in order to solve this problem? So this is kind of how it started, but then through a series of a very large series of experiments, I will say, we proceeded then to pursue the different types of process conditions with the focused ion beam. This has to do with aperture size and energy of the beam and the beam focus. Even we even did some defocusing of the beam in order to look at how to do this. So beam focus, aperture size, dwell time, lots of things like that in order to try and study how do we get to a point where we can get feature sizes that are on the order of what we need. We started out, okay, we're getting, what is it, about 30 nanometer nominal size of quantum dots. How can we work our process and control our process now so that we can get down to average quantum dot sizes in arrays that are small enough that they're going to work? And we did actually do this. And using some image analysis software, we were able to determine that our nominal size for the quantum dots in this process condition was about 8.26 nanometers. And it was very consistent from process to process, meaning we could get to a quantum confined quantum dot at room temperature in this particular material, which was tungsten, to allow us to build these devices. And so once we had this, we combined that with some of our deposition and etch processing from before in order to produce devices. And so we were able to then produce devices, but this was the point of the quiz. Now, I think Sue has this set up as a...
Yes, time to see who is listening when Dr. Bergstrom introduced what the beam is with the fibs. Is it helium, argon, gallium, or iron? And so you get to answer that question. And the second question was, what were we trying to accomplish? And the choices there are world peas, nano mountains, or designing a nearly zero current electronic device functional at room temperature. All right.
I like the nano mountains. They are kind of nano mountains.
Yeah, they kind of are. Yeah.
And people are throwing themselves at gallium for the focused ion beam, and also at choice C. They're not really choosing world peas or nano mountains. Yeah. They're choosing, and so
well, and that's probably not surprising, right? So
yeah.
So
the room temperature part is really important.
Absolutely, yes. The room temperature part totally dominates the motivation of the effort for this work. That really is the important thing. There would not be the need to get to these dimensions, honestly. If we were trying to do this at millikelvin temperatures, we could work with micron scale quantum dots and be able to get them to work. So those are like, so I guess for the first question, gallium is the dominant ion that is used in focused ion beam processing. But it's a little bit of a trick question, because it is true that other materials are also used. Now, iron is not likely to be used because it also is a ferromagnetic material, and that behaves poorly in electromagnetic focusing guns. But it is true that argon is sometimes in focused ion beams. And helium is used as a focused ion, but it's not typically used in a fib system. It's used sometimes as an implanted film or an implanted ion, but rarely used in fib. So it's possible to use it, but it's so light and has so little mass, it tends not to have much impact on the substrate, whether it's related to deposition or etch. So the heavier ions tend to dominate.
It can have some neat effects at times, though.
Yeah, it's very useful.
Of
no question. It's
amorphizing.
Not as commonly used. That's all. Okay, should we move on? What do I need to do here? Do I close the poll? Okay. Now I got to figure out how to get back. Okay, so we were able to make these devices work. So these are some images from Manoranjan Acharya and Daodan Shyam, where we demonstrated room temperature devices and demonstrated some other technologies where we put together a larger array of devices. This upper right image here shows a series of, I think there's 9, how many is there? 6? It's 8 devices that are in a ring for testing. This was done by Daodan Shyam, and some of the processes here are done by what's called reverse nano imprint lithography in order to produce features down in the kind of 10 to 20 nanometer feature range for some of these electrodes. So these were, maybe they were sub 100 nanometer feature sizes for some of the gold electrodes that were produced. But we did this, and we actually did this not just with tungsten. We actually did this also in some of the best characteristics of the devices were done with a very clever process that Manoranjan Acharya came up with in order to produce silicon quantum dots. And so we were the 6th group in the world. Okay, 6th is not first, but 6th group in the world to demonstrate room temperature SETs. So at all, room temperature SETs, only the 6th group to do that. But we were the first to produce silicon quantum dots at room temperature, or silicon quantum dot SETs at room temperature. And we were the first group to demonstrate this using this FIB process. So this was a brand new process brought to this technology, and this was a brand new brand new approach that was brought here at Michigan Tech. So
did you have to worry about the doping of it when you're dealing with the silicon ones, or do you want
the gallium doping?
Intrinsic? Yeah.
So the answer is the quantum dots don't necessarily need to have doping.
Okay.
Because we are transferring charge onto and off of, so we're inserting charge into the device or into the quantum dot. So they don't necessarily have to be doped in order to operate. And that was actually a study that we also did as we looked at the impact of gallium on the behavior of the devices, whether there was a heavy gallium loading or not. I would say that study was not totally conclusive, but it did demonstrate that there were some changes in the behavior. So there is some embedding of the ion from the focused ion beam that actually shows up in the behavior of the device. So these characteristics are a little bit complicated. So this shows a current versus voltage, and this shows what I noted earlier was this this Coulomb oscillation, where we see a periodic cycling of the current. And that periodic cycling of the current is related to these very unique quantum states that are exhibited in the system. But you also notice that it's a kind of a complex characteristic. We see Coulomb blockade under different gate conditions. You see different Coulomb blockades. So that demonstrates that this is working at room temperature, and all these measurements were done at room temperature. But it's a complex characteristic, and so we needed to understand this better. What are we actually seeing? What's the outcome that we're seeing in this? So we did some studies on that, but we also applied experimentally this device to some sensor applications. I'm a sensor builder at heart, and so we were doing some work with Dr. Craig Friedrich with Bacteriorhodopsin-based systems, and so we looked at, can we use Bacteriorhodopsin, which is photosensitive. It comes from a bacteria that's found in very briny water in some parts of the world, purified, isolated. Can we make use of this photosensitive protein as a way of producing some alternative form of a photosensor? And so we did that. We demonstrated that with BR, with a SET behavior, again at room temperature, building off of some of the work. And with one of Dr. Friedrich's students, Carl Walczak, and demonstrated very strong characteristics out from that. Demonstrated some very strong responses. We also used this as a gas sensor, where we were looking at permanent gases like nitrous oxide, and we saw that when nitrous oxide would adsorb or would physisorb onto the area of the quantum dot, or maybe it was the area of the gate, the output would the device output would recognize that charge spike as a result of the gas adsorbing and desorbing from the system. And so when we would see the nitrous on and see the nitrous turned off, we would see these changes in the charge state, and we would then get either a positive or a negative pulse as a result of the gas on versus gas off state. So it was a demonstration again that these devices have characteristics that could be useful in other areas as well. Because these are so sensitive in terms of the charge state, they can measure very, very small numbers of electrons, and that's why they're called a single electron transistor. But because these were multiple dot devices, again, we have multiple quantum dots, and because we had gaps that were modest, these gaps were probably on the order of between anywhere from 17 nanometers for the smallest devices, upwards of maybe about 100 nanometers for the larger devices. We know now we have more than one quantum dot that actually might be participating in the conduction of the device. So we needed to understand this better. We needed to study this. And so the experimental device is complex. The experimental output characteristics are complex. So we needed to understand the physics of this better. So we also needed to understand and use the scientific method in order to fully understand the characteristics of the device. So we modeled these kind of random sizes, somewhat random sizes and somewhat random spacings and positions in an electromagnetic solver in order to solve for field strengths and solve for characteristics of that transport. And so in order to do that, then we developed a method with John Jazak and two other students that contributed to this aspect of this work in order to really study the physics of this and compare it then to the experimental behavior so that we could understand exactly how these multi-quantum dot-based SETs were behaving and working. And so that study gave us a very clear indication that in all these devices, there tends to be a dominant conducting path, even when you have a large array of quantum dots that are in between. You tend to have a path that is the most likely path for the electron transport to occur in. And so if you have a most likely path,
I can see hundreds and hundreds of student, graduate student hours going into this model.
Oh, this is a stunning amount of work. There's no question. This is a huge effort on the part primarily of actually three PhD students. Two were really primarily focused on it, but Husadan Savaikar, Doug Banyai, and Pani Hazabeh did a huge amount of effort in order to understand how to do this. And but this dominant conducting path allowed us then to simplify this really complex understanding to recognize that there is a path. And if we can model that path, we can model within a fair certainty of the behavior of this device, we can model the behavior. And so we looked at this and recognized then you can model this as kind of a linear chain of quantum dots where you look at then the changes in the charge energy of those quantum dots as you change the source and drain and change the gate electrodes to look at how the control of the transport proceeds in this device. And so, yes, this is a huge amount of effort to understand the complexity of this system. Most of the research that had gone on before this work related to single electron transistors simply looked at single quantum dot devices. And so there was no work really demonstrating multi-quantum dot behavior. So we had to go very far afield in order to draw out sufficient understanding, even of more than two dots. There was some work that was being done elsewhere to show, 1 and 2 dot behavior. So this is very new, and this is built off of the collaboration with John and the students that participated in that effort. So we were able to model some of these kind of characteristics that we saw with the silicon device, these kind of paired peaks where we saw these oscillations that had, these two might have been together, but then there was a period to the next two, and then these two were together, and then there was a period to the next two, and then these two. So we saw the same sorts of behaviors that we saw back in the experimental device. And so we're able to confirm some of the reasons why those transitions were happening, some of the physics behind this. So this was a big deal to us. And some of this is as recent as just a couple of years ago, as far as kind of finally coming to this conclusion to understand the behavior here. So here's the next quiz. I don't know if this one's online or not, but this one may have more than one answer. So why do we also need modeling if we can succeed in an experiment?
Oh,
All right.
as an experimentalist. Oh.
Well, and so we've got several choices. A, it makes cool animations possible. B, we don't need modeling.
That's really true.
C, to link
I like B. I'm with B.
C links fundamental physics to observed behavior in the real materials. And that seems to be a reasonably popular choice.
Yeah.
Oh, people are choosing two answers here. D, to guide future experiments to explore potential characteristics. I would add, all right, so E, modeling should only come before an experiment, not after one. But F should be to frustrate our graduate students and keep them.
Maybe so. Yeah, probably true. Experimentalists do not like to model, and modelers don't like to do experiments. That sometimes is true.
But you have to be able to talk to each other. And that's why I think as a grad student, you have to go through both of those and understand both of those, because then like you go work in semiconductor industry like myself, I had to be able to speak both language. It's kind of different languages almost, right? Like,
Yeah.
but you have to be able to cross those boundaries. I love my modeling friends. We've done many patents together, right? Because a lot of times they can inform some cool ideas. But at the same time, I remember we were modeling some bipolar transistor one time, my first job at IBM, and I said, well, what shape should we make it? What shape should it be? He says, I don't know. I can make it whatever shape you want. I can put Mickey Mouse shape in there if you want.
Yeah.
And I was like, okay, that's not helping. I don't want a Mickey Mouse shape.
Yeah. Well, sometimes that's you were saying earlier, Tom, you said, how do you model an elephant? Maybe
Yeah.
sphere, right?
Yes. Assume the elephant is a sphere.
Assume an elephant is a sphere.
Yes.
No. So the primary answers that I wanted to get to are C and D. So you really have to understand how the fundamental behavior of the device and how the observed behavior in the real materials, the real device, links to the physics of the system or links to the chemistry of the system. And that really does guide the future direction. And so I would argue that modeling doesn't always come before an experiment, because sometimes you have a starting point for modeling, but the model is incomplete because the experiment demonstrates a behavior that is not previously understood. And so sometimes you have to take a step back and say, what didn't we understand about this device or about this characteristic that we have to understand in order to be able to communicate clearly what it is that we see? So that's the reason why I would argue that E is not the case. Modeling is great when it does come before an experiment, because it gives you a starting point to try and understand what it is that you want to demonstrate. But sometimes the behavior is so complex that you cannot demonstrate it. It is true that you can make cool animation.
My favorite is when they iterate on each other, right? So you have an idea, you model it. It's probably crap, but it's a good place to start. You build it, it refines the model.
That's the ideal case, when you have an experiment that supports the modeling, that supports the experiment, that supports the modeling.
We've gone through, in my semiconductor experiences, we've gone through that many, many, many times. And I never trust the first model other than for an idea. But as you develop confidence with it, it really can help you out, even if you are only concerned about building it.
Well, that is basically my talk. So the next slide is just simply my concluding. So I wanted to just confirm and say in the end that, the scientific method helps us frame the challenge. Models help define the expectation. The experiment, it really helps you understand what is the right pathway, and both are necessary to understand the behavior. And I think we can learn some life lessons there too, right? That we don't always take the right path, but we can find ways to learn from it in order to find the right path. And so I would encourage us to recognize how we can make use of some of these logical paths. So.
All right. Yeah, no, Paul. So thank you so much. I'm going to share my screen and share a few slides just very quickly. And I encourage the audience to start loading any questions you may have, or if you just want to make a salutation to Tom or to Paul.
I see Andy Gross in the house. Did you see that, Dr. Bergstrom?
No, I didn't. Hey, Andy.
So Andy, post a hello or a hello. All right, so I want to acknowledge that this evening's presentation has been sponsored by Virgil and Lucille Davis, and we thank you so much. If anyone would like to sponsor a Husky Bites, you are invited to do so. 100% of any sort of sponsorship goes directly to support student scholarships. The minimum contribution is $100. The maximum so far is was contributed by about 15 different people, which was the hockey night, and that was about $1,700. So all this money is being cobbled, just it's going straight into the Student Scholarship Fund. We usually Facebook Live this. We did have a fail last weekend. We don't know why. We think it had something to do with Zoom bandwidth, but these are, if you're ever not able to actually join us via Zoom, you can also join us via Facebook Live. We didn't launch that poll. I do want to do a shout out to next week's Husky Bites webinar, which is being given through the Honors College. And so we have Mary Raber, who is the Assistant Dean of Academic Programs for the Pavlis Honors College. She's the Director of Global Leadership. She's the co-director of Husky Innovate. This will be conducted with co-host Brad Turner, who will be joining us. So next week, you're gonna join us to learn about solving wicked problems. And once again, if you would like to ask a question, all you need to do is type a short message into the Q&A feature. And so Steve Camp, you raised your hand. Does that mean you want to speak? Because I can invite you to be a webinar speaker. Just send me a chat if you would like to be a speaker. I can invite you to be panelists. And so right now we're going to shift to the Q&A. And so Tom, can you see the Q&A?
Yes, I see it over here.
All right.
I was just going to put in a plug for, I don't know, another little known fact, perhaps. Last week, I realized was Tim Havens.
Yes.
Do you, he and I go way back.
Yeah, he was a student probably in your time.
Well, because of music?
He was he was the bass player in the jazz band, and B, he was my TA in one of my classes as well. But we went on jazz tour and everything together as well. So
well, yeah, no, he of course gave an amazing webinar, and all of these things you can view kind of going to the past. If anybody's out there wondering what they should major in, this is a great way to kind of learn a little bit more about a few other things. So Tom, go ahead and just kind of like, we can take turns. You take the first question, I'll take the second question.
I saw
take them in any order.
I did my little call out there. I saw as soon as I started reading it, I saw the 3M sticky call out as the example of the successful failure.
Yeah, that is a great example, and it's been shown up as a marvelous example of an experiment that didn't go as planned, but actually turned out to be a really useful outcome. And that's the way experimental work can be. So
so as a scientist, sometimes that's horrible, right? You're like, oh, I thought I was going to do a thing and the thing didn't work. But as an engineer, like I try to wear my engineer hat as much as I can, where like, well, that was interesting. How can I use that for something, right? Mm-hmm. And my favorite example of that, so Paul, Jin's research work with you was on porous silicon. And one of my favorite stories from that was about the guy who made porous silicon. So you have silicon with a lot of surface area, and then tried to etch away the porous bits of it and put it into like KOH or ammonium hydroxide or something. And the sample exploded because there was so much surface area that the reaction just like took over and it destroyed the sample. Yeah. And they looked at that like, well, that was unexpected and interesting. And so they like patented the idea of using porous silicon for like self-destructing chips.
Yeah, and it actually has been used as a device that's called a squib, which is basically an igniter.
Oh, yeah.
So it's been used as an electronic igniter where you pass current in the presence of oxygen, and you can actually cause it to spontaneously oxidize.
Oh,
it does it exothermically, so it acts like a fire, basically.
Yeah.
The surface area is so high for nanostructured porous silicon. The surface area to volume is so high that it will spawn. The oxidation rate is so high it'll actually burst into flames if you have enough oxygen around. So
Do you see another interesting one, Janet?
Well, I would say, you know, I know we have undergraduates, students listening, and future students listening. So this question is for an undergraduate student: what's the best major for a career in nanotechnology? And what was each of your undergraduate majors?
Well,
you
so I knew
doubling?
by the
No.
age of 16 I wanted to be an electrical engineer. So I kind of fell into this pretty early on in my career. So there are some areas that are probably more strongly driven by kind of nanoscale, but the reality is every engineering discipline has some aspect of research or activity that is at the nanoscale, and every aspect of pure or applied science has some kind of nature that is associated with, you know, nano and atomic scale work. So I think there's a lot of overlap, and so it maybe depends on your appreciation and interest in chemistry, or it depends on your appreciation and interest in kind of physics as it relates to solid materials, or physics as it relates to gases, or physics as it
No,
relates to something
it's
else.
absolutely true. No, and my, you know, like
Janet, you were material science?
Materials, yeah.
yeah, I wandered. I started in chemical engineering. Well, I was, you know, I was good at math and chemistry and stuff like that. So I started, well, it's a long story, but I wandered. I wandered through chemical engineering into material science, and fell in love with metals, you know, and oxidation. I mean, I just think it's you. That's the fun thing about being sort of in the sort of technological sector, is you can follow, you know, what you end up being interested in is what you end up being good at, right? And then you
Sure.
sort of go in that direction.
Sure.
So,
But I just put a little shout out to the materials world. So I knew early on that I wanted to do electrical engineering, but then starting with grad school, and then even more so when I got into the working world, I really started to appreciate the material science aspects of the semiconductor world a lot. So I kind of got a lot more into that. There are people I know that have built entire fabulous careers on just studying the interaction between silicon and metals, right? Like just like pick your favorite metal and how does it interact with silicon? Does it diffuse into it? Does the silicon diffuse into the metal? Do they mix? Does it form a silicide? Is it what phase of silicide is it, right? Like all of these really interesting things that, like, I'll say I like if I had to do it over again, I think I would probably spend a little. I don't know if I'd switch to material science, but I'd spend a little more time over there than I did.
everything is made of something, right? And so, you know, as material science and engineering is the intersection of chemistry, physics, and engineering, right? So at this point, usually right around 7 p.m., I thank the audience. So I just want to thank everyone for joining us. We had 125 live attendees. What this turns into is like 1,000 attendees over time, because these talks are posted. Thank you so much for listening. I was noticing so many new names out there. So I think the EE crowd really kind of showed up. Well, and so we will stick around till 7:15, and then I call a hard stop because people have to eat their dinner. If you know, because I need to eat my dinner. I guess that's what I'm saying.
Well, there's some great questions that are.
I see some really good one about
All right,
careers
Tom,
and
you go ahead.
employers. There's one
You
here
go ahead and
about
pick some.
what kinds of careers and employers do people who focus on nanotechnology end up with? And I think that again is like almost like the material science discussion, where it is like all over the place. And like I've kind of wandered with my career a little bit too. I've wandered now into photonics, and that is a really interesting area. So like the nanotechnology, everybody always thinks about the semiconductor industry, but Paul, you were a MEMS guy, right? Primarily MEMS. which are really cool devices and still hot. Your phone probably has what, 6 or 7 MEMS devices in it, I think.
Yeah, the microphone, the accelerometers, yeah, all kinds of stuff.
The screen, like you just look at any technology device and you'd be like, okay, the screen itself is just the glass is an engineered product,
Right.
right?
Yeah.
So those of you who are out there who don't know what a MEMS device is, you can see how quickly ECE people fall into jargon. I'm just saying.
Yeah,
sorry.
So,
My children, you know, with my wife and I, my children are basically doomed.
Are they using jargon in the kitchen?
Yes, there's jargon in the kitchen and with homework, and they correct their teachers with things about like that.
So I guess I would say though, kind of nanotech scope things, there is a lot of things associated with the electronics industry, microelectronics, and kind of esoteric materials that relate to sensors and things like that as well. So some of that might kind of fall more toward chemistry or fall more toward optics. A lot of optical materials are engineered nanoscaled materials. So dielectric lenses are a great example of that. So, and they are pervasive. I mean, dielectric lenses are used everywhere. So, so there's a lot of different things. So if you're interested in something and you think it might have a nanoscaled impact or implication, the chances are it does. The chances are there's something associated with it. So.
Janet, I really like this question from Zach about if he's in high school and is thinking about going to, or he's going to Michigan Tech, and then he's already thinking about a doctorate and like how to go get on a path to that. And I just want to say, I had absolutely no plan to get a post-bachelor's degree. I got into engineering world because I was selling cell phones and I thought those were really cool. And I wanted to learn about how to make them. And I thought Motorola made great products and I wanted to go work for Motorola. Long story short, I worked at Motorola as an intern one summer. It was great. I had a fantastic time. And then I met Paul because I literally went knocking on doors of faculty I knew.
Office doors, yeah.
Literally knocking on faculty doors and saying, hey, I'm really interested in doing something and I could use some money. But I'm really interested in doing something. Is there anything I can do in research groups around that, you know, to kind of get involved in stuff and, you know, do something real, right? Because again, I'm a builder, experimentalist guy, right? And I kind of fell into Paul, and basically I finished my senior design program and I finished my senior year working with Dr. Bergstrom, and Paul was like, so you're going to grad school.
I told him.
He told you.
I told him.
Yeah. So you're going to grad school. You don't have to stay here. That's fine. But you need to go somewhere for grad school.
Yeah, I told him, you need to go to grad school.
Yeah.
Maybe not a PhD, but you need.
All right, I'm just going to echo that. I think that I think, well, so I just want to state something. All right, going to grad school. So for the Bachelor of Science degree, we pay for it. For the master's and PhD degree, they pay you and they pay your tuition, assuming you've got a decent GPA. And decent does not mean rocket scientist. It's generally anything above a 3.0-ish.
Good enough. Yeah.
So grad school is totally in reach for many people. And so this is a person who's in high school now. I would say to them, knocking on the doors in a pandemic means sending emails to professors, I think that's what that looks like. So
yeah,
and I think trying to find ways to get engaged early. Absolutely.
Engaged early.
Yeah. In an area, get engaged early.
And I honestly, like, it's kind of scary because they're the professors and stuff, right? But
now look at us.
No,
look at us. We're not scary.
No, they're not. Like even me. So I was a TA, right? I haven't been a faculty, but I did TA work and I had a lot of students as a TA. And you know, you have these office hours and whatnot. And so often it's like crickets, you know, and you're like, you have to be there. You have office hours. Like, I loved when people come to talk about stuff during office hours. Like that was like why you're doing this. right? Like there's no
Well,
fun in grading. There's no
right.
fun in writing exams.
Right.
But
And so in office hours, you can ask stupid questions, quote unquote, stupid questions. You can say things like, how do I get involved in undergraduate research? You can say, you know, what suggestions do you have for me for taking classes next year? I know you're not my advisor, but I'd love your, what your thoughts are. You can actually ask other questions. You could say, I tried this homework and I have no idea. I have no idea how to solve this, how to even get started. Right?
Yeah.
I mean,
Almost every faculty will give you a path forward.
yeah.
I can't think of anybody that wouldn't.
Yeah, but don't expect to be like sitting in your dorm room and then like, oh, somebody comes and like, hey, you should do this now. Like that's not going to happen. Like you got to go hunt and find and figure it out.
So there was one person that clearly knows me or has had me in class that just asked a question. So number one, missing from my introduction, I speak Klingon. I speak a little.
yeah.
Number two.
Paul, speak some Klingon to me.
Here we go. Success.
Okay.
Anyway.
Okay, thank you for translating.
So they asked about a 10 kilovolt supply. There's a lot of conventional and unconventional ways where they produce very high voltages. There is a lot of buck transformer kind of work that is used to get to those kind of voltages. So it's a complicated answer, so I won't go too far into that. But the last question, that's the one that caught my, so somebody has really good eyes. They were looking at the modeling slide and they said that the current axis scale had 10 to the minus 20 amps, whereas some of the previous scales were in picoamps.
Picoamps, yeah, most of us picoamps.
Is 10 minus 12. So modeling versus experiment, that is one aspect of a difference. But the short answer is these devices should be able to demonstrate basically the transition of charge from one or a few electrons. And so the scale that was shown there relates to a model where the number of electrons model was not, the number of electrons that were used in the model was maybe not at the scale that was the same as what you might see in an experiment. But it is also true, though, that these devices, we have seen characteristics of these devices down in the attoamperes, which is 10 to the minus 18. So 10 to the minus 18 amperes is less than 10, that's less than 10 electrons. And the answer is you can really measure less than 10 electrons on some instruments.
Whew. That's really impressive. Well, and I just want to share a personal anecdote. While sitting here on my butt, I actually achieved my move goal. So I don't know if anybody can explain that to me, but
well, you're very animated at times, you know. That
apparently, I waved my arms around. Yeah. So Catherine notes, great talk, Paul. What's beyond silicon and Moore's law?
Yeah, there's a lot of things that are going on right now, and oftentimes what they're doing is they're trying to find ways to add three-dimensionality to build complexity while not necessarily pressing geometries of devices down smaller. We are very close to some fundamental limits for MOSFETs. The feature sizes for the what's the latest Apple processor out of TSMC? 7 nanometers, and they're working on 5 nanometers. You can't go a lot smaller. You can, but you can't go a lot smaller and still have a MOSFET behave like a MOSFET. So there's only so far that they can go with that. So what they're starting to do is what is actually a discussion that started 30 years ago, trying to find ways to stack devices and stack devices and stack devices. So instead of having just one layer of active electronics in an electronic chip, now maybe we can end up with 30 layers of active electronics in an electronics chip. So instead of, 12 billion or 20 billion transistors on a substrate, maybe you have 20 billion times 30 layers on a substrate in order to add complexity. That's where things are going.
I can say anecdotally, for ages, the packaging engineers in the semiconductor world were kind of the ugly stepchildren. You know, like look at me, I'm going to make my awesome chip. Now you small people go package it for me. And
Hard
it-
area.
You just
it's
need
very
a
hard, but it
packaging
was like,
engineer.
you're just it's just putting it into a package. Like, come on, how hard is it? And now I found that anybody that has any sort of background in any kind of packaging has a job right now. Like there are no unemployed packaging people right now, because the packaging is becoming such a bigger part of it. Like the focus,
Oh, it's
the eye
interesting.
of Sauron has moved a little bit from like, how do we just shrink everything, like Paul said, into
Well,
how do
and
we.
didn't you say photonics testers were pretty hot too?
That's also like I just put like photonics test on my resume, like one little line, like learning on working to figure it out, sort of, kind of, basically, right? And yeah, it turns out that there's a massive shortage. I went to one conference. I went to a conference, and because I wanted to learn, like I was like, I'm new to this, I got a handle on it, but I want to go figure out like what are real people doing. So I went to this conference, and there was like 10 people that were just wandering around, and if you looked like you knew what you were talking about, they hand you cards like, call me if you want a job, call me if you want a job. Like I walked away with like a stack.
Yeah, but you
So,
love living in Albany, and you don't want,
well, that's right now because I work for a Silicon Valley based company, but my role is really truly remote. So I get to stay in Albany in a, I wouldn't, not necessarily low cost of living area, but low to medium cost.
Yep.
And I get to have my cake and eat it too, basically, right? I get my Silicon Valley.
This is one of the very interesting things about being an engineer in a pandemic is you've got a lot of options. You've actually got a lot of flexibility.
And hiring and firing is like, it's going on like crazy. Like people are changing jobs, they're quitting jobs and taking new jobs in the middle of a pandemic, like nothing,
That's
no
just
problem.
nuts.
My company has hired, since the pandemic, they have remotely onboarded at least 20 people, 20 new people. Like remote
All
onboarding,
right.
like in the mail comes your computer and welcome.
All right, I just want to share a few compliments. So Ward says, if I were in person, it would be a standing out ovation. There's been a few other compliments that I've sort of posted. Really, really, really nice job, Paul. A quick question from John. What are the major challenges to commercializing quantum dots?
Yeah, I was actually just trying to type in an answer to that, but I think it'd be better if I say it. So the reality is there are a lot of challenges to it, and there's a lot of people that try to manufacture quantum dots, and it's really then a matter of what the application is. So quantum dots, because they're small, are very sensitive to charge state. So if you have them in air and they're in a bottle that has a surface charge on them, you can't just pour them out and put them in something. They're going to stick to the bottle because they're going to get charged, and they're going to stick to whatever charge. So they tend to be very sensitive to that. So oftentimes quantum dots are distributed in kind of in a solvent is a way of managing them and holding them if you buy commercial quantum dots. So the surface charge state, huge issue for almost all of them. Now, maybe not all of them, but almost all of them. And the distribution of size is a huge problem because the behaviors depend on the dimensions very critically. And if you have too broad a range, if your Gaussian curve is too broad, you end up with you end up too large of a distribution, and you don't get what you expect to get in terms of your behavior. So the consistency of behavior and just the management of the quantum dots as you work with them are major things. And that was actually one reason we didn't go with just buying commercial quantum dots off the shelf, because distributing them on the surface is not an easy process to do. It's been done, people have done it, but it's really, really hard to do.
All right, so we're right up on 7:15, which I've called a hard stop because we have had some of these go on to 7:30, and that's just too long. That's just too long. Yeah. So I want to personally thank Tom at Wallner. It's been wonderful to to get to know you through a rehearsal and now a live performance with, you know, a concert musician. Paul, you know, I know, you know, it was nice to hang out with you again. It's absolutely wonderful to learn about your accomplishments and the accomplishments of your graduated students. And again, to just learn more about the field. Audience, please join us next week. These are every Monday. We start chitter chattering at about 5:40 p.m. We sort of get serious around 5:55, and then we sort of get a little bit serious, and then we get less serious as the evening goes on. And this is the highlight of my week. It's wonderful to connect with you. Thank you so many EE alumni, because there's so many names out there I haven't seen in a while. I think there's quite a lot of people, Paul, who may have graduated from your group, or just be a friend of a friend.
Size. Yeah, they're pretty large number that have.
If you reach out to me, I'll send.
But I'm glad that they came. So
I can send you a list of who is here if
Okay.
you'd like to kind of reach back with them. Yeah. Good night, everyone. Thank you, Sue.
Yeah, thanks
Sue
Thank you,
is
Janet.
Husky Bites. Thank you, Tom. Thank you, Paul. Good evening.
Talk soon.